Welcome to the first module of the game theory class. My name is Kianoosh Boroojeni, and I'll be happy to instructing you in this course. And the first video that you see is about the introductory module of the game theory class. All right, let's look at the outline of the lecture. First, I'm gonna show you some game theory definitions with the help of the game of chess. We mainly look at the definition of game situation, strategy, winning strategy, and then I'll talk about the determinacy theorem of the game of chess as one of the earliest results of game theory, and then we're going to try to prove it mathematically with the help of multiple tools. Mainly, we see the game tree, which is a data structure that you will see later, and then with the help of the method that is very common to prove things. It's called induction, but not regular induction. It's called a strong induction. Strong induction would be an extension of regular induction that I'll show you, and you'll see how to use both game theory and strong induction to prove the determinacy of game of chess. The reason I choose chess, or the textbook, our textbook uses chess in the first module, is because it's a perfect information game, and there's no chance moves, and it is finite under bounded play assumptions by FIDE, and also it's a game that has familiar rules. You all probably know how pieces move and how the rules of the game is, so that's a good fit for the first module. We use chess to illustrate the definition of a strategy, definition of winning a strategy. Also, we use chess to model a game formally. I'll show you how to formally model a game using some mathematical tools and definitions. Also, we're going to look at one of the earliest results in game theory by John von Neumann, who is very famous in computer science generally. And the theorem basically talks about the determinacy of the game of chess, which basically says either white, which is the first player that makes the first move, has a winning strategy, or the black, or the second mover, has a winning strategy, or each player has a strategy guaranteeing at least a draw. So you'll see this is true, and we can prove this mathematically. The main question is basically, by looking at this theorem, must chess be a win for white or win for black, or should be a draw by force? So you'll see how to prove this theorem in a formal fashion. All right, let's dive a little bit into the game of chess. We have two players. We call them white and black because they use different colors of pieces. White is the one that moves first, and then black moves second, and then we have alternating turns. The initial setup is you have 16 pieces for each player, 16 white pieces, 16 black pieces, and the rules are fixed. We know how like each piece moves. I don't want to repeat it because it's a little boring if I want to do that. And then there are three possible outcomes. You either have a win by white, that means the black king is checkmated, or a win by black, that basically means the white king is checkmated, or we can have a draw. Let's quickly look at the draw conditions. We have five possibility for a draw in the game of chess. One is a stalemate, which basically means the player who wants to make a move has no legal moves, and therefore we call that a stalemate. That's a first condition of draw. The second one is mutual agreement, like one player offers draw by just moving their hand toward the next player in a real chess setting, and then the other player either agrees or disagrees. If it agrees, then they will have a drawn game. The other condition is 50 move rule, which basically says if two players make 50 moves without moving a pawn or without capturing a piece, then we have a automatically drawn game because we don't make any progress in the game of chess if we don't move the pawns or if the pieces aren't captured. So it's better to stop it. And then the other condition is threefold repetition. That means if one position of pieces happen 3 times in the match, that's a drawn game. You cannot repeat the same position 3 times. If that happens, you have a drawn game. And then finally, if the board position prevents victory by any of the sides, then we have a draw. For example, if one side has a king and a knight and the other side has a king, it's theoretically impossible to checkmate the opponent's king with only a knight. The same thing happens if you have a bishop instead of a knight. But if you have both knight and bishop, then you can checkmate. Or, for example, if you have 2 knights in one side and the other opponent has no pieces left other than the king, that's again another impossible situation. You cannot checkmate the opponent. We have insufficient materials to checkmate the opponent, so that's another condition for the draw. One property that we want to focus on for the game of chess is that the game is finite. What does it mean? That means every play ends after finitely many moves. There's no infinite move game. You play starting from the initial position, and then after a number of moves, the game ends either in a draw or a win by one of the players. Even if the number of moves is astronomically large, it's going to eventually end. And the reason we'll focus on this assumption or this property of the game of chess is because we're going to use it for the induction proof that you will see later. But just remember that in this table, I have kind of summarized the length of game of chess, either the average serious games that happens between players in real world. The average number of moves is 30 to 40 moves per side. That means you can have up to like 80 moves if you consider the total number of moves for both players. And that's a typical length for a game of chess. But the longest recorded real game, it happens in 1900s, would be around like 500 some moves total, which was very, very long. But the theoretical maximum that is possible to show, but it's a very long process to show the theoretical max. But based on the FIDE rules that I showed earlier about the draw conditions and all that, we can have about 17.7 thousand moves in total, or 8,849 moves per side. And then if you consider no 50 move rule that I mentioned earlier, or no threefold repetition, then we can easily see that the game can be unbounded, or it would be infinite. Why? Because the players can just move let's say they can move knight back and forth, and then don't care about each other's kings and just don't focus on checkmating the opponent. Just they move their bishop or knight back and forth forever, and that's going to be a boring game that lasts infinite number of times. But if you keep the threefold repetition rules in place and 50 move rule in place, then you're going to end up with a much shorter length, around 17.7K. That's a finite number of moves. Later, if you try yourself, after I show you the definition of game situation, you can come up with your own upper bound on the length of the game of chess and how many moves are possible. You're not going to end up with this small upper bound. You may end up with some astronomical number, but that's enough for our discussion, because what we care about is the game is finite. We don't care like what's the minimum upper bound on the length of the game of chess. Before we get to the nitty-gritty of modeling the game of chess and showing you all the mathematical formulas and mathematical symbols, I'd like to quickly define the winning strategy in an informal way. The winning strategy is a strategy that guarantees the victory for one of the sides, independent of the opponent's choice. So that means if you have a winning strategy in the game of chess, even if you play with the world chess champion or if you play with the strongest chess engines in the world, you're gonna win. Right? Whatever they do, you just move the pieces based on the winning strategy, and you're gonna move. I mean, you're gonna win. And then we have another strategy that is not as strong as winning strategy. We call that a strategy guaranteeing at least a draw in a game. And if you have that strategy in hand, then you can at least get a draw. That means you can draw the game or win the game against any player or any chess engine in the world, no matter how strong they are. All right, so let's define the game situation in a more formal fashion for the game of chess. This is a definition that can be extended to some similar games as well. A game situation is a finite sequence like the one that you see, x0, x1, all the way to xk, where x0 is the opening position, and each xk in this sequence results from a legal move applied to the previous situation. So think of X's as snapshots of the chessboard, which has 64 squares and like 32 pieces originally, and then you gradually remove the pieces because the pieces get captured, and the game continues and advances. But every snapshot, the kth snapshot, results from the legal move applied to the previous snapshot, k minus first snapshot. So xi in this example, in this definition, is basically a snapshot of your chessboard, or the position of all pieces on the board. But if you want to focus a little bit more on this definition, because we have two players in this game, then the turns are changing alternatively. That basically means all the moves from even indices to odd indices should be played by white. So going from x sub 2n to x sub 2n plus 1 should happen uh, by a white move, by a legal move from on the part of the white. And the opposite, from an odd index to an even index, the transition from x2n minus 1 to x2n position should happen because of a legal move on the part of black. Why do we say legal move? Because not every move is legal. You cannot just move a piece in any random location and say this is a legal move. And you can check out these boundaries, or these ranges for n for both white and black. I put them in a way that they make sense, assuming that white is going to make the first move and k is the total is the index of the last position in the game. These ranges make sense. I don't want to get into details of it, but you can try it yourself. Replace k, the capital K, with some number, and you can check out that these boundaries or these ranges for n make sense. So, long story short, this is the definition of a game situation, which shows you the history of all the positions of pieces on boards. And if k is even, the capital K is even, that basically means black makes the final move. And if it's odd, that means white makes the final move. Because if you end with x1, for example, that means only white have moved once. But if you end at 2, index 2, if capital K is 2, that means black made the last move, because you have k0 to k1 happens because of a white move, and k1 to k2 happens because of a black move. And that's how it works. Before we move forward, I'm going to show you an alternative definition for the game situation for the game of chess. The one I showed you earlier is not really the best definition for the following reason. A lot of people consider chess as a Markov game, which basically means the future evolution of the game depends only on the current state, not on the entire history of game. And it's kind of obvious because if I show you a chessboard and ask you what the best move is now, you should be able to tell me without knowing what has happened in the past or how did we get into this position of pieces. With the current state, you can decide for the future of the game, and you don't need to know the entire history. But if you remember, if you saw in the previous definition, which was mentioned in the textbook, and that's why I showed it to you first, it says the game situation should be a sequence of all the board positions from x0 to the current or to the end. So from very beginning to the end. So that doesn't really make sense with the Markov game property of the chess game. So I'm going to show you a more common and commonly used definition for the game situation for the game of chess. And this is the definition that is widely used and the chess engine uses in some ways to store a game situation or game state for the chess. It looks a little scary because it has it has four pieces of it's a tuple of four elements, but if you pay a little attention you can understand them. You have O, T, C, and E. I'm going to explain each one of them briefly. What is O? O is a function. We call it a square occupancy function that shows you the position of pieces on the chessboard. Basically, this function will map every square to a piece that occupies that square. And if no piece occupies the square and the square is empty, then we're gonna map that square to an empty set, which is a special element that basically means this square is empty because there's no piece on it. The other one is T, which basically shows the player's turn to move. It's either white or black. So we all know that the turns will be changing alternatively. So that's the turn. C would be the castling rights. If you know the game of chess good enough, you know that during the game of chess, there are four castling moves are possible. Either the white king can castle or the black king can castle. And each of the kings can castle either short or on the king side, or they can castle long or on the queen side. So we have four castling rights. That's why you see this castling rights would be an element of true false to the power of 4. That means it should be a tuple of 4 flags. Each flag is either true or false. The first flag is for white king's king side castling or short castling of the king side of the white king. The next one is the long castling of the white king. The next one is the short castling of the black king. And the last one is the long castling of the black king. So you have four different castling rights. We just specify them in this game situation element. The next one is the en passant target square, which is a very tiny detail in the game of chess. You probably haven't heard of it if you are not familiar with the game of chess in detail, but it's some move that can capture a pawn by another pawn under some certain scenarios. But the reason that we need to bring the E en passant and C castling rights into the game situation is because we're going to define the chess game as a Markov game. We don't want to store the whole history of moves. And that's the price you need to pay. You need to make your game situation a little more complicated if you don't want to store all the positions from very beginning to the current position. You need to store a few other information. In this case, we store T as turn, C as castling right, and E as en passant. Target square, which is either a certain square. S is a set of all squares, all the 64 squares, or it can be empty. That means there's no ampersand possible. But the squares, the ampersand squares or the ampersand target squares will only be on the third rank or sixth rank. If you're interested in knowing what ampersand means, you can Google that. I don't want to waste your time on that. But basically, the ampersand move capture a piece, capture a pawn that makes two-step advancement from the second rank to the fourth rank for white, or from seventh rank to the fifth rank for black. And then the pawn that is sitting on the fourth rank, the black pawn that is sitting on the fourth rank, can capture the white pawn that has made two-step advancement in the immediately next move. That's the definition. So this is the alternative definition that I'm providing for the game situation, and that's the definition that I'm using for the proof of determinacy of game of chess that was introduced by von Neumann. Let me quickly talk about the square occupancy function, because that's kind of important and it helps you understand the future slides. Basically, this is a function whose domain would be S, which is the set of all 64 squares we have in the game of chessboard. I mean, in the chessboard, and the target would be T union empty, which basically means the piece type set, which can be either white king or black king, or white queen or black queen, or white rook, all that. Union empty set. Empty set is part of the target, because if the square is empty, we're gonna map it to the empty set by the occupancy function, by the square occupancy function. So that's the function. S is the set of 64 squares. Normally, in the chess game, we define squares using a file and a rank. Each file and each rank have its own label that you'll see on a chessboard. Files are basically the vertical columns that you see on a chessboard. We have 8 of them. They are labeled as A, B, C, D, E, F, G, H from left to right. As you see in this picture, it's clearly specified that we have 8 files from A to H, and ranks are basically the rows or the horizontal arrays that basically are labeled with numbers from 1 to 8. The white side is starting from 1, the black side starts from 8. And basically, as you see here, the set of all the squares is the Cartesian product of A to H file set times 1 to 8 rank set. When you multiply them with Cartesian product, you will get all these labels for the squares. From A1 all the way to H8, you have 64 different combination of file and rank, and that's how you name a square. If you name a square, you need to start with the file label and then the rank label. That's how you label the squares. And then for the piece type T, we have a similar situation. It's a Cartesian product of the color set and the piece type. We have 2 colors for pieces, either white or black. So that should be multiplied with the Cartesian product by the type of a piece, which is either king, queen, rook, bishop, knight, and pawn. So these letters represent the piece types. When you multiply them, you have a 2 element in the first color set, and then you will have 6 elements in the piece type. 2 times 6 will give you 12 different piece types, and then the set T will have like 12 elements. Now, why do we call O a function? Because you cannot place more than one piece on a single square. It's impossible. There's no way, right? So O of S for a given square S will represent the piece type on that square. Or if it's empty, then O of S would be equal to the empty set. Now let's look at the practical implementation of the game situation that I mentioned in the previous slide. Um, it's proposed by Forsyth Edwards. We call it the FEN or Forsyth Edwards notation because of them. And it's widely used by chess engines like Stockfish. It has 6 fields rather than 4 that I showed you earlier because it has to like contain more information, especially for the 50 move rule that forces a draw. But it's very similar. I'm going to quickly show you what those six fields are. One is the piece placement, which is basically the same as O function that I just showed you. The other one is side to move. That's showing you the turn, either white or black, similar to the T parameter I showed you. And then castling right, similar to C that I showed you. And then you have en passant, a square target that I just showed you earlier. But the other two extra fields that this one has, and I didn't show you in my the definitions, are half move clock and full move number. The half move clock basically gets reset after every single pawn move or piece capture, because those are the events that show the progress in the match. And if this progress doesn't happen and the half move reaches to the 50 value, that means we should have a draw because of the 50 move rule. And then full move number basically gets incremented after every single move. It starts from 1 and then shows the total length of the game. Here's an example for x0, the complete representation of complete state representation for the game of chess using FEN string, using the FEN notation in the initial position. That's true for all the games. As you see, we start from the 8th row or 8th rank, I should say, this rank, and we write down all the occupants of squares, starting from left to right, from file A to file H. As you see, R means rook, and because it's lowercase, that shows you the black rook. If it was uppercase, that would be the white rook. And then N means knight, although knight is written as K-N-I-G-H-T, but we don't use K to represent knight because K would be used for king, so knight is represented by lowercase n for black piece, and for white piece would be capital letter N. And then you have bishop B, Q queen, K king, B bishop, and knight, R rook. So this is basically showing you the occupant of this row. For the next row, it would be 8 pawns. So you see 8 P's. Each P represents these 8 pawns. And then you have, by the way, between two ranks, you see a slash. The slash basically separates one rank from the next one. And then you have a slash followed by 8. 8 means you have 8 consecutive empty squares. You can represent them with a single number. That's going to save you some time instead of using dashes to represent all the empty squares. And then you have like empty ranks from rank 6 all the way to rank 3, because this is the initial position and no pieces have moved even once. And after that, you see all the white pawns with 8 capital P's, and then the white pieces from rook all the way to knight, bishop, queen, king, bishop, knight, rook. And then after this a string before piece placement, you see the side to move. W means white needs to move because white is always the first mover. And then it shows you the castling rights. Castling right would be, complete. All the four castlings are possible. Both white king and white queen can make their moves. And then the en passant is empty because there is no en passant possibility because no pawn has moved yet. So it's impossible to have an en passant. Then 0 would be your half move clock, and 1 is your initial value for the full move number. So that's how it looks. All right, so let's define a strategy in a formal way for the game of chess. A strategy is a complete plan of action. Mathematically, if x represents all possible piece positions, then the white strategy is a function like SW, which gets a history of piece positions. We call them a game situation in the textbook, from x0 all the way to x2n. And that's the input of this function. The output would be um, an element or a piece position in x. X is the set of all piece positions that are possible in the game of chess. For the black strategy, we have a similar definition. It's going to be a function. We call it S sub B. B means black, W means white. And again, same thing. The domain is the sequence of chess piece positions from x0 all the way to x2n plus 1. That's a situation in which the black has to move. And the target is x again. That basically means the output of this function would be the next piece position that is proposed by this strategy. You may say, why we have 2n here and why we have 2n plus 1 here? The answer is the white strategy only dictates the white moves, so you need to have 2n positions or 2n index in the last position before you make a move with white. And for black, you need to have a 2n plus 1 index of piece position before you make a move. That basically means, the turns are alternative, and that's why this is the definition. Now, a strategy would be a pair of both white and black strategies. So if I have a strategy for white side and for black side, the pair would be called the strategy, a complete plan of action. And that plan of action pair of strategies will define the whole game. If you know these two, then you can play the whole game from beginning to end in a deterministic way because you know these two functions. If you want to just say it in a more layman term and less mathematical way, you can say a strategy by a side shows a legal move at every situation when that side wants to move. And this is basically the definition in the textbook. But if you assume that xi represents or it contains enough information that we don't have to go all the way back to the initial position and say xi represents the state or the situation of the game, similar to the FEN string that I showed you earlier, then you can define the white strategy and black strategy in much easier fashion because these are strategies for the Markovian game of chess. And then in that case, you can say both domains for the white and black should be x. So x is both the domain and the target for both of them because knowing only one state or the last state is enough to decide for the next move. You don't need to know the history. But again, you need to choose the definition that has 4 tuples or 4 fields, not the definition in the book that I defined first. Now that we have seen the definition for strategies, let's define the winning strategy. I'm going to define it for white, and then for black would be similar. I don't need to mention both of them. A strategy S sub W is a winning strategy for white if for every strategy S sub B of black, the play of the game determined by the pair of SWSB ends in victory for white. That means no matter what strategy black chooses, the winning strategy of white is going to win the game. Right? That's basically uh, consistent with the informal definition I had for the winning strategy in the previous slides. And then we can say SW is a strategy guaranteeing at least a draw for white if the following thing happens. For every strategy SP of black, the play of the game determined by the pair of SW-SP, the whole strategy for both white and black, ends in either a victory for white or a draw. That's what at least a draw means. That means we either have a draw or white wins. You can define the winning strategy and a strategy guaranteeing at least a draw for black in a symmetric fashion. I don't want to waste your time on that. Finally, let's use those definitions that we have seen to present and prove a theorem, which is very interesting. And it's the theorem for determinacy of chess. It's one of the earliest results of game theory. So it's good to see them historically speaking and understand like how game theory works. You have a bunch of definitions first, and then you make a theorem, and then you try to prove the theorem using some mathematical tools. In chess, that's the theorem. The theorem is about chess. The determinacy of chess basically says the following. In chess, in game of chess, one and only one of the following must be true. And we have like three outcomes. One, white has a winning strategy. Two, black has a winning strategy. And three, each of the two players have a strategy guaranteeing at least a draw. Okay? Now you may say, okay, so which one is true? You're saying one of these three should be true, but which one, right? We have seen a lot of advancement in the game of chess and artificial intelligence and neural networks, and you all know like AI is booming right now. But even with the current boom of AI, we cannot find out which of these three is true. That means even if you're talking about the most advanced or strongest chess engines in the world, you cannot guarantee a win for white, or you cannot guarantee a win for black, or you cannot guarantee a draw. That's how it is, right? It shows you how complicated the game of chess is, right? And you may say, well, this is kind of obvious. It's a trivial theorem. You either have a win by white or win by black or a draw. Is that trivial? Why do we even call this a theorem if it's that trivial? The answer is no, it's not that trivial. If you go back and think about the definitions that we had provided for the winning strategy or the strategy of guaranteeing it's a draw, you will realize that this is not trivial. Why? Because a winning strategy should win every single match against any chess player or chess engine with any strategies. Right? That's a very strong statement, and that's why it's not trivial. What tools do we need to prove? We need to show you two tools. One is the strong induction tool. That's a method of proof that is similar to induction, but it's a little bit more advanced. And then the other tool would be a game tree, which is a data structure that is very useful in a lot of games, and we'll see it in the future as well. So the first module of this course is a good place to remind you of a lot of mathematical tools that we need in the future. One of them is proof by induction, not regular induction, but strong induction, which is the extension of the regular proof by induction. We call it the proof by weak induction, the regular one, and this is the strong induction, the extended version. I'm going to briefly mention what it is and show you how it works with a simple example. It proves a proposition P of n, where n is a natural number. The proposition is a sentence or a statement that is either true or false. That's what proposition means. The base case in this example, because the domain of n is all natural numbers, the base case should prove the proposition P of n for the lowest value of n. In this case, the lowest value of n is 1. So the base case basically proves that P of 1 is true. Then you have inductive step. In order to show you the inductive step, you need to first understand the inductive hypothesis. And this is the only difference between a weak induction and a strong induction. In the strong induction, we assume that for every arbitrary k in natural numbers, where k is a capital number, capital letter, the P of k is true for every lowercase k less than or equal to the uppercase k. That means for any arbitrary value, let's say k, the capital K is 100, we assume that our proposition is true for all numbers from 1 to 100. This is the strong induction. What was the inductive hypothesis for the weak induction that is more popular? For weak induction, this should be only focused on the k, on capital K, not every lowercase k less than or equal to k. For example, if capital K is 100, the weak induction only assumes that the proposition is true for number 100. But the strong induction assumes that it is true from all numbers from 1 to 100. That's the difference. But both the strong and weak inductions are true, and there are legitimate tools that can prove statements like this, like the proposition P of n for every natural number. What is the inductive step now that we know the inductive hypothesis? The inductive step says, given the inductive hypothesis, tries to prove P, our proposition, for n equal to k plus 1, capital K plus 1. That basically means now that we know if capital K is 100, now that we know all the numbers 1 to 100 will make our proposition true, try to prove the same proposition for number 101, which is the next number. And if you are successfully proving the inductive step and the base case, then you can claim that you have proven our proposition for every single natural number in the world with no limitation. You have proven P of n for every n in the world. Before I use proof by strong induction in our example for the chess game, let me show you a very simple example so you understand what it is and how it's different from a regular weak induction. So let's say you want to prove that any integer greater than or equal to 2 can be a factor to its prime factors, can be factorized, and you can get all the prime factors of a number. This is a theorem that you have used many times before, and this is the basis of the whole number theory. So what does it say formally? It says for every n greater than or equal to 2, for every n belongs to the natural numbers greater than or equal to 2, n can be written as a product of prime numbers. That's how you define it in a formal fashion. The proof is going to be based on a strong induction. The base case targets the smallest value in the domain. The domain is all numbers greater than or equal to 2, so we're going to prove the claim for number 2. And this is trivial because 2 is a prime number. P of 2 obviously is true because 2 can be written as a product of itself. You don't need to have any other prime number other than 2. So it's a trivial statement. So the base case is done. They're halfway true. The other half of the way to finish the proof is to prove the inductive step. The inductive step assumes the inductive hypothesis. So let's see what the inductive hypothesis says. This is the inductive hypothesis. What does it mean? It means that if you think about a capital K as a random number in this domain, domain of all natural numbers greater than or equal to 2, we assume that any number less than or equal to capital K and greater than or equal to 2 can be factorized to prime numbers. It can be written as a product of prime numbers. That's your hypothesis. What do you need to prove in the inductive step? You need to prove that capital K plus 1 is also prime. Is also satisfying the statement which says K plus 1 can also be written as a product of prime numbers. In order to prove that, I'm going to use another method of proof that is used very commonly by mathematicians called division into cases, or breaking down the proof by different cases. I'm going to consider two possible cases. Case 1 is when K plus 1 is prime. Case 2 is when K plus 1 is composite. If the K plus 1 number is prime, then the statement is trivial for K plus 1 because K plus 1 can be written as the product of itself. That's it. But if it's composite, it's not going to be that trivial. But because of the definition of composite numbers, you know that K plus 1 can be written as a product of two numbers A and B, where both A and B are between 2 and capital K. This should be capital. What does that mean? If K plus 1 is composite, then it is divisible by a number other than 1 in itself. That's why the reason is, if it's composite, then it's not prime. So some number between 2 and K, including 2 and including capital K, will divide K plus 1. Let's say that number is A. Right? Then how do you get B? B would be the quotient of dividing K plus 1 by A, because K plus 1 is divisible by A. It has a quotient. That quotient is B. So longest story short, you can write K plus 1 as A times B, where both A and B are between 2 and K. Now, given our inductive hypothesis, both P of A and P of B are true. That means what? That means you can write A as the product of a bunch of prime numbers, I call them P, and B can be written as the product of a bunch of other prime numbers, I call them Q. P and Q are just placeholders for a bunch of prime numbers. Therefore, you can say K plus 1, which is your target that wants to be factorized into prime numbers, can be written as A times B. Now I'm going to replace A with this product and B with this product. So I can write this like this. And say, okay, I don't need 2 pi's here, just 1 is enough. So I can write K plus 1 as the product of all prime numbers that are in the factorization of A and in factorization of B. And that's the end of the inductive step, because I have finished both base case and inductive step successfully. Then I can say my proof is complete. The next tool that you need to make the proof and complete the proof for determinacy of game of chess is a very common data structure. We call this the game tree, that represents a game and its dynamics. As you see in this picture, which is in the textbook, we have a tree. By tree, we mean the tree in computer science, with multiple vertices and edges, and one vertex is called the root on the top. In this case, it's going to be the opening situation or the opening position, and then you have a bunch of game states or game situations in the following levels. And the branches are representing the moves, either the white move or the black move, depends on which level we are. That's very useful for a lot of proofs, including the one that I'm going to show you next. So the root of this tree represents the opening situation x0, where the pieces are placed in the original initial position, and no move has been made, and it's white turn to move and all that. The other vertices represent other game situations that can happen because of some legal moves, starting from the opening position all the way to any moment in the game of chess. Leaves, which are on the lowest level possible and have the highest distance or furthest distance from the root, are terminal outcomes. Terminal outcome means either white wins or black wins, we call them decisive outcome, or we can end up in a draw, as I mentioned before. So these are the leaves that are on the lowest level. Now, what is a tree path? A path in a tree, based on your data structure course, you know that in a tree, a path is defined a sequence of nodes starting from root all the way to the descendants of root. And for example, I can say this is a path, like starting from root, and then you just come to the child of root, and then the grandchild of root, and then grandchild of root, all the way to a certain point. That will show you the move history, because you will have a sequence of chess situations or chess states that's going to give you the move history. And then if this path continues from root to a leaf, that would be a play of a game. That means you can represent the whole game from start, when you have a opening situation, all the way to the end, when either a player wins or we have a draw. What is the branch? The branch is showing you the legal moves. Right? For example, in the opening position, we have 20 different moves. So the root has 20 children. Why 20? Because you have 8 pawns. White has 8 pawns. And each pawn can be moved in 2 different ways, either 1 advancement or 2 square advancement. So 2 times 8 would be 16. You have 16 possible legal moves by white pawns. No other piece can move other than pawn and knight, because they are confined within themselves, and they are smothered with their own pieces, except for knight, because knight jumps over the pawns. And the knight can we have 2 knights. Each knight can move twice. We can move in 2 different ways. For example, the white knight at square b1 can move to a3 or c3, and that basically means this knight has 2 moves, the other knight has 2 moves. 2 plus 2, 4. 4 plus 16 possible moves for the pawns. You will get 20 moves in total. So the parent has 20 children, but at some point during the middle game, you can have about 30 to 40 moves. That's the average based on the history of all moves in the archives that are maintained by different websites. And the typical maximum in a real game could rarely reach to the 60. That means you may have one vertex in this tree which has 60 children. That happens rarely. It's normally not that much. But you can create a theoretical scenario that gives you the absolute theoretical max, in which one vertex can have up to 218 different children. That's a lot. I don't want to show you like how this is possible, but there's a way to create this 218 theoretical maximum number of children for a vertex. And that means that one moment in the chess game, you have 218 different legal moves. And that shows you how complicated the game of chess is, because the player should think about all possible moves, not only the first move, but the subsequent moves. That's why chess game is very difficult. The grandmasters are crazy people. All right, now what's the average length of a game? As I mentioned before, you have like 70 to 80 moves, because each side plays somewhere around 35 to 40 moves. And why do we care about these? Because I need to find out what the height of this tree is. The longest real game has this many moves, as I showed you before, but the theoretical max with the 50 move rule would be around 17.7 thousand. That basically means the height of this tree would be around 18,000, which is a super long tree. And the branching factor B is limited to 218 in a theoretical fashion. So you will have a tree of size that is unimaginable, super large. It's the size of the tree would be b to the power of h, which is less than this number, 218 to the power of 17,700. That's the upper bound. It's a lousy upper bound because it's super large, but that shows you how big this tree is. But regardless of how big it is, it's finite. So we can study that because it's finite with a finite height and finite branching factor. We can study it, right? But can you store it somewhere? No, this number is astronomical, and no computer can store the whole tree. It's like ridiculously large. All right, I'm gonna make two quick definitions in this slide, and then we're gonna go forward. One is a definition of a subgame, which is represented by gamma of x, capital gamma of x. That basically means part of the game is starting from the state x. So, for example, if I call this chess state x, the subgame x would be a subtree rooted at this node, and that means I'm only focused on this part of the game. If you want to consider the whole game as a subgame, you can call it the gamma of x0, where x0 is the root. So the whole game would be a subgame of the x0 position, which is the opening position. But you can define subgame for every single state of the game, which is every single vertex in this tree. And that would be the subtree rooted at that vertex. And then we need to do one more definition. Let's represent or denote the number of vertices in a subgame with root x using n sub x. So n sub x would be the number of vertices in the subtree rooted at x. And therefore, the number that I got earlier, 218 to the power of 17,700, is a lousy upper bound for n sub x sub 0, which is the number of nodes in a subtree rooted at x0, which is our tree root. Okay, now we are ready for seeing the proof, because we have seen all the tools that are needed for the proof. I'm going to use a strong induction on the number of vertices of any subtree rooted at game situation x. So that's the parameter of my induction, the number of vertices of a subtree. The proposition that I'm going to prove with strong induction is, given any arbitrary game situation x, the subgame gamma of x with nx vertices is determined. What does determined means? It means that either one side has a winning strategy, or both sides have at least have strategies that guaranteeing at least a draw. Okay, so first of all, why this is the proposition that we need to prove? Because if you prove this for any arbitrary game situation, this arbitrary is important, just to highlight it, then you can replace that game situation with x0, x sub 0, that would be the initial game situation. And that would prove the determinacy of chess, because you have proven that gamma of x0 is determined, and gamma of x0 is the whole game of chess. So that's why this is the proposition I'm interested in proving it. What would be the base case if I want to use strong induction? Well, you need to assume that you have a subgame with the minimum size. The minimum size of a subgame or subtree would be 1. So that basically means you need to first prove this for leaves, right? So if x is a leaf, which represents a win or loss, or a win for white or a win for black, or a draw, a terminal situation, then we need to show that it's determined, right? Which is kind of trivial. And then you need to prove the inductive step. That means you need to prove the determinacy of a game by assuming the determinacy of its subgames or subtrees. Because, you know, if you remember in the strong induction, we assume that the same claim is true for all the problem of a smaller size or all the games of the smaller size. Now you need to prove it for a game that has a bigger size. How do you do that? We need to use inductive hypothesis and a bunch of logical statements that can prove that. I'm going to start with the proof of base case, which is kind of trivial, but let's look at it. If n sub x is 1, that means if you have a game situation whose subtree or subgame has only one node, that means you're dealing with a leaf. That means x is a leaf. And therefore, based on the definition of the game tree, x represents one of the three situations. Either we have a draw, that means both sides of the subgame have some trivial strategies guaranteeing at least a draw. What do they need to do? Nothing. So both SW and SP would be empty set because they don't need to do anything. It's just a draw. So there's no more action in the game. So they just have to sit and watch each other. Don't do anything. But that's going to satisfy the definition of a strategy guaranteeing at least a draw. So the pair of strategies would be empty set, comma, empty set. That's going to guarantee a draw. It's so obvious that it's hard to understand. The second possibility is when you have a white king is checkmated. That means you have a decisive result. Black is 1, so black has a trivial winning strategy. What does black needs to do? Nothing, because white king can now move, and you know that's it. So the black king just have to watch and enjoy the win. The other scenario is when black king is checkmated. That means white has a trivial winning strategy, and that strategy would be empty set as well, because black king is already checkmated and there's no legal move for black, so white doesn't need to do anything. So the proof of base case is trivial. All right, now let's look at the proof of inductive step, which is not going to be as trivial as the base case, but it's not that complicated. In order to show you that, I need to start with the inductive hypothesis of the strong induction. And here it is, my inductive hypothesis. It says for any arbitrary k, integer k, from 1 all the way to nx0 minus 1. What is nx0 minus 1? nx0 is the number of vertices in the whole tree rooted at x0, which was the initial position. That was the root of the whole tree. Minus 1, because I don't want to exceed the boundaries after I add k by 1. So we say for that arbitrary k, let's assume that if n of x is less than or equal to k, then the subgame rooted at x would be determined. What does that mean? That means if the number of vertices in a subtree representing the subgame rooted at x is less than or equal to k, then that subgame, which starts from the position x and goes all the way down, will be determined. That means we will have either a winning strategy for white, or we have a winning strategy for black, or we have strategies guaranteeing a draw for both sides of the game. The goal is to prove that if the number of vertices is k plus 1, then again, that sub game will be determined as well. So we already know all sub games with the size less than or equal to k are determined. Now we're going to prove it for k plus 1. That's the whole thing. That's the whole inductive step. And just to make things simpler for ourselves in the future slides, let's make one more assumption. Let's assume that there are B legal moves from the current game situation X, where B is greater than or equal to 1. That basically means the next branching factor, the number of legal moves that you can make in the current position, is finite, which we have seen there was a maximum 218 before I show you, but it's limited and it's going to be at least 1. Why should it be at least 1? Because if there's no legal move, then we have a stalemate, and a stalemate is a draw, and X should be a leaf, but that's not possible because the number of nodes in the subgame should be at least 2, because k is at least 1, 1 plus 1, k plus 1 is at least 2, and so it's impossible to have a leaf. So X is not a leaf, therefore it has at least one child. So that's why we have this situation. And this diagram clearly shows you the whole story. We have X as the parents, and the children, we have B of them, x1, x2, all the way to xp. And as you see, I have used the green box to show that these are all determined. Why are they all determined? These green boxes, because we have the inductive hypothesis. So inductive hypothesis assumes that all of them are determined. For the sake of simplicity and without the loss of generality, I'm going to assume that we are on the even level. X is on the even level, and that means it's white to move next. Even level means, if the root is at level 0, level 1 would be the children of X, the children of the root, and then level 2 would be the grandchildren of the root. And because we are having alternative moves, when you're on an even level, it's white's turn to move. And if you are on an odd level, it's black's turn to move. What I'm going to show you in this proof is on the even levels, but you can symmetrically do the same kind of discussion for the odd levels and prove it for the black side of the game. But anyways, we're going to focus only on the white side, and we're going to assume that X is on an even level. That means it's white turn to move next. Let's assume that there are B legal moves, as I showed you in the previous slide, and the children of X are represented by x1, x2, all the way to xb. These are all the legal states that will be available after you make one of those B legal moves starting from state X. Now, for each I from 1 to B, for each of those children of X, the gamma of Xi, that means the subgame of Xi, will have less number of vertices compared to the X. Why? Because the subtree for X contains everything that comes below X, all the descendants of X. And for Xi, we only focus on one of the subtrees that are connected to X. So obviously, the number of nodes in Xi subtree would be less than the number of nodes in X. Why does it matter? Because now that we know this is the case, we can use the inductive hypothesis and say, for all the children, we have a determined game. That means there's a winning or losing strategy for white, or there's a draw strategy. But there's no losing strategy. I should say there's a winning strategy for white, or there's a winning strategy for black, or there's a strategy guaranteeing both draws. So based on the deductive hypothesis, we know that the subgame gamma of xi is determined, and that's why I put those green labels in the previous slides. Now I'm going to continue the proof of the inductive step by showing you three separate cases. Because it's impossible to do it in one case, I have to break it into three separate cases because it gets a little difficult. The first case is when there's a particular I from 1 to b. That means there's a particular child of x called xi, such that the subgame gamma of xi has a winning strategy like this, SW with the label I, for white. So there's a winning strategy for white in the subgame xi, gamma of xi. If that's the case number one, then I can simply say the gamma of x can also be won by white using the following winning strategy. What's the winning strategy? If you're on the position x, all you need to do is to move to the position xi. How do you do this? You need to add this move to your strategy. If you remember, the strategy was a function that moves you from one game situation to another game situation. So when you add this order pair, x and xi, to the winning strategy at xi, then guess what? You move to the xi, and xi guarantees a win for white because we assume there's a winning strategy on xi's for white. So this is the new strategy. If the state is not equal to x, just copy whatever the white winning strategy says for xi, and for the game state x, output xi, go to xi so you can win after that. So that means because white should make the next move, white chooses the good move that guarantees a win for itself. The second case of the proof of inductive step is very similar to the first case. It says, let's assume that case 1 is false. So remember, case 1 was one of the children of x must have a winning strategy for y. So case 1 is false. There's no such xi. But there's another I, there's a particular I, such that the gamma of xi, that means the subgame starting at xi, has a pair of strategies, SW, SP, I, guaranteeing at least a draw. So that means one of the children will have a pair of strategies that guarantees a draw at least for both sides. In that situation, I can claim that the gamma of x, the subgame of x, is guaranteed to be drawn using this strategy, where the black uses the same strategy as xi, but white should change it a little bit. The white strategy should be the same strategy, the same strategy guaranteeing at least draw in xi for every game state other than x. And for the game state x, white should go to a game state xi because xi is going to guarantee an at least draw. So this strategy S prime coupled with SPI will guarantee a draw. So white should make the next move, go to xi, and then in that state, we have a subgame that is determined, and it's going to guarantee at least a draw for both sides. The last case of the proof by induction in this theorem proof is when case 1 and 2 are both false. So if case 1 and 2 are both false, that means none of the children of x will have winning strategy for white, or will have a pair of strategies guaranteeing a draw for both sides. That will imply that for every child of x, xi, the subgame xi has a winning strategy for black. Because of the inductive hypothesis, for every subgame is determined. So if you don't have a winning strategy for white, or you don't have a strategy for draw, therefore you should have a strategy for a win by the side of black. That winning strategy for black is represented by SPI. So SP sub I, or superscript I. Okay, so what? In other words, in this situation, the third case, white is hopeless because no matter which child of x it goes to, that child and the subgame rooted at that child will have a winning strategy for black. So we can generate the following strategy for black to win the whole game. So gamma of x is guaranteed to be won by black using the following strategy. The strategy, I call it S prime, which is the union of the following sets or functions. If C is a descendant of xi in the game tree, then we are going to choose its next move using the winning strategy SPI. So for subtree x1, we're going to choose the moves from the first strategy, first winning strategy for black. For the second for the second child x2, we're going to choose it from the second winning strategy for black. For the third one, we're going to choose from the third winning strategy for black all the way to the last one, xb, where the next move is going to be determined by the last winning strategy for black, S sub b superscript b. And in this example, in this case, no matter which move is played by white, we end up in a game that has a winning strategy for black. So, but the black should be careful and choose the right winning strategy based on the next move of white, right? And that's it. That's the complete proof. We have proven both the base case and inductive step. And inductive step was proven in 3 separate cases because it was a little bit difficult. And that concludes the proof, because guess what? We have shown that the game of chess is determined using proof by strong induction. And that's the good place to stop. Thank you.